Hey, welcome back to Algebra 2. This is Unit 5. We're going to take a brief little break from our lessons, and I'm going to insert a little lesson here on simplifying radicals. This is something that I don't usually like to devote an entire lesson to, but I think it fits in nicely here, and it's going to help us with what we're about to be doing. So let's go ahead and go through this. So first of all, just by review, the square root symbol is asking it's the inverse of a squared. It's asking the question, what number times itself is equal to 16? Well, that number is 4. So that's the value. On number 2, it asks for the square root of 24. So it's asking us for a value, a number that when you multiply it by itself, you get 24. Well, there's no integer that does that, and it turns out that it's not even a rational number. It's a non-terminating decimal, so kind of like pi. It's a number in between 4 and 5. Well, what we can do, though, is we can express this as a more simplified radical if possible. So not always, but sometimes we can. So let's take a look at how that's done. We take the number 24 and we make a factor tree. And so we start by thinking, well, what number is multiplied to 24? And it doesn't matter if you use two factors and I use two other factors, we'll end up with the same prime factors at the end. So I'll use 4 and 6. And then I can go further with 6 and say that's 2 times 3, but I can't go any further than that because 2 and 3 are prime. And notice that I'm not using the trivial factor 1. Okay, so what we're saying here is that 24 is 2 times 2 times 2 times 3, and it certainly is. 2 times 2 is 4, times 2 is 8, times 3 is 24. So I'm going to rewrite this exactly like that. Oh, I'm missing a 2. The square root of 2 times 2, well, that is known, or the square root of 2 squared, if you will, is just 2. 2 times 2 is 4, and the square root of 4 is 2. And the square root of anything times itself is just itself. So this has a square root of 2. So I'm going to say 2. Then the square root of, and 2 times 3 is still in there, we'll say 6. It's important to realize that I can only take the square root. Let me review this. I can only take the square root of, if I have 4 and 6, I can say that that's equal to the square root of 4 times the square root of 6, which is 2 root 6. But if it was 4 plus 6, I can't do that. It can only distribute this square root over multiplication or division. Let's look at this next one. 5 root 36. Well, the square root of 36, we can figure that out. That's 6. 6 times 6 is 36. So this is just 5 times 6, which is 30, and there's no more square root left over because we were able to take a perfect square root. 2 root 18. Well, the square root of 18 is not a whole number, so we're going to have a square root over, but maybe we can simplify. Can't always, but let's try. 18 is 9 times 2, and 2 is 3. Excuse me, 9 is 3 times 3. So I got this pair of 3's there. So 3 times 3 times 2. So for every pair, I get to bring out 1. And when it comes out, the square root of 3 times 3 is just a 1 3. So for every pair inside, I get to bring 1 out. And 3 times 2 is 6. So this is 6 root 2. Because that's all that was left over was the 2. All right, the square root of 72. Let's do that one. 72. Let's see, that's 9 and 8. And 8 is 2 and 4, which is 2 and 2. 2 is prime, though, so we stop there. And 9 is 3 and 3. So the square root of 72 must equal, we're picking just the leaves of this tree, just the very bottom row. Everything that doesn't have some come out. So I don't take the 9 or the 8. So 3 times 3 times 2 times 2 times 2. All right, well, we can take the square root of 3 times 3, and we can take the square root of 2 times 2. So I get to bring out 1 3 and 1 2 to the outside, and what comes on the outside multiplies together. So 3 times 2 is 6. So that value is 6 root 2. All right, let's go to the next one, 108. Let's see here, 108. Well, let's see, I can divide that by 2, right? 54 and 2. That's 6 and 9, right? And then 6 is 3 and 2, and 9 is 3 and 3. So it looks like I've got a couple of 3s here and a couple of 2s. So I'm just going to, instead of rewriting it, I'm just going to go ahead and bring that out. I can bring out 1, 2, because I had a pair of 2s under the radical, and 1, 3. And remember, everything that doesn't come out, all these leaves that don't come out, they get left over. And everything on the outside multiplies together, making this 12 root 3. Okay, so when we multiply radicals, it's actually pretty easy. You just multiply outside numbers with outside numbers. And we multiply inside numbers with inside numbers. And then we try and simplify if we can. So 3 times 5, well, that's 15. That's on the outside. And on the inside, we have 2 times 3 is 6. Now we can try and simplify the 6, but as we just saw, it's 2 times 3, and there's no pairs to bring out. Okay, square root of 3 times the square root of 3. For many reasons, I want you to automatically know that anything, the square root of something times the square root of itself is always just itself. The square root of 3 times the square root of 3 is the square root of 9. But the square root of 9 is 3. That's what, this is squaring a square root. That's what this is. That's the square root of 3 squared. Any way you want to look at it, it's all 3. So if you see the square root of 5 times the square root of 5, I want you to immediately say, well, that must be 5. Okay? All right, let's go on to number 9. So I just talked about 5, right? 2 root 5 times root 5. We know that root 5 times root 5 is 5. So this is just 2 times 5, which is 10. Okay, so all right, we got a negative number. No big deal. We just have to make that negative 12. Then inside with inside, so that's 3 times 5 is 15. And again, 15 is only 3 and 5, and those are prime, so I can't do anything with that. Let's go down to this one. 5 and 3, well, that's 15. 10 and 2 is 20. Well, now 20, that might be able to be broken down. Let's try it. Well, there you go, 4 and 5. 4 is a perfect square, so we know we can do it. It's going to be a pair of 2s in there. So we'll have a 5 on the inside. I'll bring out a 2, and 2 times 15. Remember, when the 2 comes out, it multiplies with what's already out there, making it 30. 5 divided by the square root of 2. Okay, well, traditionally, we do not leave square roots in the bottom of fractions. So what we're going to do is we're going to rationalize the denominator. That's what that's called. It's called rationalize the denominator. And this helps you make sure that you get the same answers as other people, and it just helps you communicate your work to be able to do this. So rationalizing the denominator. I did not write that very clearly at all. This is an important word. Let me spell it out. Get lazy with these electronic pens, don't I? Rationalize the denominator. All right, so the way you do it is quite simple. You just multiply on the top and bottom by the square root you're trying to rationalize. So I multiply by the square root of 2. So the top becomes 5 square root of 2. And the bottom, well, we just talked about this. Root 2 times root 2 is 2. And so that's it. Let's try another one. 2 divided by the square root of 3. I'll simply multiply the top and bottom by the square root of 3. This gives me 2. Root 3 over root 3 times root 3 is 3. Okay, so that's what happens when you have a radical in the fraction. Well, what about if you have a fraction in the radical? Well, remember I said we can't distribute square roots over addition or subtraction, but we can multiplication and division. So to take the square root of a fraction, you simply square root the top and square root the bottom. So you'll hear me say, how do I square root a fraction? Square root the top, square root the bottom. And that's it. Let's do the next one. Square root of 8. So square root of the top. So the square root of the top is 8. And the square root of the bottom is 3. The square root of the top is square root of 8. Okay, but we can simplify the square root of 8, right? So that's 8. Becomes 2 and 4, which is 2 and 2. So it's got a pair of 2s. So this is 2 root 2 all over 3. All right, let's try the next one. Okay, how do I square root a fraction? Square root the top, square root the bottom. 2 is the square root of the top. The bottom is the square root of 3. But we don't like square roots in the denominator, so we'll rationalize the denominator, giving us 2 times the square root of 3. Root 3 times root 3 is 3. Okay, well, what about adding radicals? Well, you have to add radicals the same way you add variables. They have to be exactly the same. They have to be like terms. So you can think of this as like, this is really similar in concept to saying 2x plus 5x. You would say 2x plus 5x is 7x. Well, same thing. 2 root 3 plus 5 root 3 is 7 root 3. But the root 3's don't change, just like how the x's didn't change when we added them. Oh, but I can't do number 18. I can't add root 72 and root 18 because they're not the same. But if we simplify them, maybe we'll get lucky. So 18 is 9 and 2. And the square root of 9 is 3, so this will become 3 root 2. We'll take it all the way down and I'll show you. See, you have a pair of 3's here. So it's 3 root 2. Now 72 is, let's see here, 9 and 8. 9 is 3 and 3. And 8 is 2 and 2 and 2. So I got a couple of 2's there and a couple of 3's there. So I get to bring out a 2 and a 3, which is 6. So this is 6 root 2. Well, now they are like radicals, so it's 6 plus 3 is 9 root 2. All right, let's try the next one. I've got 4 root 14 over 2. Now, the square root of 14, I cannot simplify. That's just 7 times 2. There's nothing I can do with that. But how do you divide something that's got a radical in it? Well, the rule is, just like with multiplying, you can divide numbers on the outside with outside, numbers on the inside with inside, and that is it. So I cannot divide the square root of 14. I cannot divide this number inside of 14 by 2, but I can divide the 4 and the 2. Now, if I had something like 2 root 7 on the bottom, let me just show that as a different example. If I had 4 root 14 over 2 root 7. Well, then I could divide. I would divide 14 by 7 because they're both in the radical, making it root 2. But that's not what this problem had. This problem didn't have that, so I leave it alone. Square root of 48 divided by 4. Well, let's try and simplify 48. 48 is 8 and 6, which is 2 and 4, which is 2, 2, and 6 is 2 and 3. So I got a pair of 2's. And another pair of 2's. So I have 2 2's, so that's 4. I can bring out 4. 2 times 2 is 4. And then left over the 3 on the bottom. Under the radical. And look at that, the 4 is reduced. So it's just the square root of 3. 10 minus the square root of 12 over 2. Okay, there's nothing I can do here because this is a 1 here. And I can't divide 1 by 2. And if I'm going to distribute this, I want to be able to divide both of these numbers. If I'm going to try and reduce, I have to be able to divide both of them. But we might get lucky with the 12. So the 12 is 4 and 3. And 4 is 2 times 2. So they can rewrite this as 2 root. We're going to bring out 1, 2 for the pair. And now I can divide. Now I can divide 1, 2, 3. Don't touch the root 3. That's in a radical. But 10 and 2 divided by 2 gives me 5 minus 1 root 3. And I don't need to write the 1. All right. Well, occasionally you're going to come across situations where you need to rationalize something like this in the denominator. And the way we do that is by multiplying by the conjugate. We've already talked about that some, and we'll talk about it more later. But the conjugate is when you have the sign in the middle switch. So it's the exact same thing, the sign in the middle. Earlier we simplified radicals and I said, hey, just multiply by the denominator. Remember that? Root 2 over root 2. But when you have a number plus a radical or a number minus, you have to multiply by the conjugate. So my top will become 5 minus 5 root 3. And this is going to be our difference of two squares pattern. I'll go through and show it so you can see it, but I have to FOIL this. 1 times 1 is 1. 1 times the square root of 3 is a negative square root of 3. The square root of 3 times 1 is square root of 3. Square root of 3 times negative square root of 3 is negative 3. And then those cancel out. So this ends up being 5 minus 5 root 3 all over a negative 2. All right, let's try this next one. I've got 2 minus root 5 over 1 plus root 5. So I'll multiply on top and bottom by 1 minus root 5. And again, I have to foil, but this time I have to foil both of them. So I'm probably not going to fit in this little bitty area here. Let me get rid of that. So foil. 2 times 1 is 2. 2 times the negative root 5 is a negative 2 root 5. Negative root 5 times 1 is a negative root 5. Negative root 5 times negative 5 is a positive 5. On the bottom, 1 times 1 is 1. And these should cancel out. I should have no radicals when I'm done. 1 times a negative root 5 is a negative root 5. Positive root 5 times 1 is a positive root 5. Root 5 times negative root 5 is a negative 5. And those are gone. So if I combine like terms on the top, 2 plus 5 is 7. And then I have a minus 2 minus 1 is 3. So minus 3 root 5 all over a negative 4. Okay, last little concept I want to talk about is when you're taking the square root of variables, the square root of an even power variable, we can actually bring some of that out. So x to the fourth is x times x times x times x. So it turns out that there are 4 x's here, which means we have 2 pairs of them. So I have to bring out an x to the second power. In other words, I'm dividing that exponent by 2. Y to the second means y times y, so I got a pair of y's. I can bring that out. But I actually need to bring it out in the absolute value. I'll explain why in a second. Then on the z cubed, I got a z times a z times a z. So I can pull out one z, but I still got a z left over. So why do we need absolute value around the y? Well, let's just look again at the square root of y squared. Well, what if y were negative 2? If I plug that in for y, I would get a negative 2 squared, which is 4, and the square root of 4 is 2. See how it magically removes that negative? That's because we're squaring it before we square root. And square root always gives a positive number. You just don't take the square root of a negative. So that's why we needed the absolute value, so that we're being completely accurate with how this would evaluate. And that's it for this little lesson on simplifying radicals.